In this tutorial, we're looking at circle theorems. First, there are a number of theorems that you need to learn with reasons, and then we need to know how to apply these theorems to exam-style questions. Typically, exam-style questions will contain one or more, normally multiple circle theorems in the same question. So it's important you have an understanding of all circle theorem rules. The first we're going to look at is if we have an angle at the centre of a circle and the angle at the circumference. The angle at the centre is twice the angle at the circumference. And that is if they are within the same arc. Now, an arc is a section of a circumference. The next rule is if we have an angle in a semicircle. Angles in a semicircle are 90 degrees. So where your triangle or your angle at the circumference, if that is a semicircle, now we know it's a semicircle because the line has to go through the centre of the circle. That needs to be the diameter for that rule to be true. The next, angles from the same arc in the same segment are equal. Angles in the same arc in the same segment are equal. So, an arc, as mentioned, is a section of the circumference. Our segment, think of like a segment of orange, it's part of that circle. So that's to say if this angle is A, this angle is also A. And also that is true for this angle being B, then this angle will also be B because they are also on the same arc in the same segment. Next is if we have a cyclic quadrilateral. Now, a cyclic quadrilateral is a four-sided shape inside your circle. Each of the corners of the four-sided shape need to be on the circumference of the circle. It's not just any four sides anywhere. They have to, each four corners need to be at the circumference. And the rule here is that the opposite angles in your cyclic quadrilateral sum to 180 degrees. So if we have A, B, C, D, that's to say A plus B equals 180 and C plus D equals 180. Next is if we have a perpendicular line from the centre of a circle to a chord, it will bisect the chord. So there's some keywords in there we need to know. Perpendicular means at right angles. So here is the centre, we have a perpendicular line. Now that is going to a chord. Now the chord is this one here. This is a chord. So it's a line that goes from one point on the circumference to another point on the circumference, but not through the centre. And then if we have a line that is perpendicular coming down from the centre to that, it's going to bisect. Bisect means to split in half. So these two dashes here mean each of those sides are the same length. Next is if we have a radius that meets a tangent, that will be at 90 degrees. This is a really common circle theorem. So a lot of the time with circle theorems, if you do identify a radius that meets a tangent, now a tangent is a straight line that touches the circumference. If it meets a radius, the angle that that would make is 90 degrees. From an exam technique point of view, if you see this rule, just label the right angle on. Even if you don't know how to answer the rest of the question, label that right angle on and you're going to get a mark for that. So this next one is very similar to what we've seen before, but what we've got is a tangent and a radius, another tangent, another radius. Now two tangents drawn from a point on that circle are equal. So what that looks like is we've got right angle from the rule above, and then this line here and this line here will be equal in length. So we could, a really common one is split this down the middle, and what you've got is two congruent triangles. Finally, the last rule is the alternate segment theorem. Typically this one is the most difficult to be able to spot. So the angle between a tangent and a chord is equal to the angle at the circumference in the alternate segment. Bit of a wordy definition, but actually if you are asked to state your reasoning, just stating the alternate segment theorem is enough for the mark here. Now what we're saying is your angle at your tangent, so this one here, so the angle between that and your chord, now this is your chord because it's not going through the centre of the circle. So the angle between your tangent here and your chord, so this angle, is equal to the angle at the circumference, here's the circumference, in the alternate segment. Now how I like to think of this is a bit like the parallel line rules and the alternate angles. It's very similar in that, I believe, here's my little technique. If you draw your Z, it will always point to the angle that is equal to the angle on the inside of the Z. Now this is something that I've just made up, but it does always work. Let's look here. If you spot your Z within a circle theorem, the angle on the inside of the Z here will be equal to the angle that it points to, which is this one here. And just stating alternate segment theorem is enough. So let's have a look at some exam style questions, putting this into practice. Our first question, B, C and D are points on the circumference of a circle centre O. A, B, E and A, D, F are tangents to the circle. Okay, we've got to think tangents to the circle. We know about that 90-degree angle. Work out the size of angle ODC. So let's find ODC first. ODC, we're finding the size of this angle here. Now what we know straight away is that this is the radius. This is also the radius. OD and OB are the radius. So we know that this angle is 90 degrees and we know that this angle here is 90 degrees. Now it might help us, it might not. This angle is 90 degrees. Now, what we've got is this angle here being 40 degrees. Let's see what else we can work out from that. So, why are they telling us this angle is 40 degrees? So, let's work out, if we know we've got the circle theorem where these two lines are equal, so now we've got a 20 degree angle. So we've got 20 degrees and 90 degrees. So that is 180 degrees minus 110 degrees. That leaves us with 70 degrees. We know this angle here is 70 and we know this angle here is 70, giving us a total angle here of 140. Using the rule that angles at the circumference, or angles at the centre of the circle, are twice the angle at the circumference, if that's 140, we know that's going to be 70. Now all of these things may help us, they may not, but we're just using the angles that they've told us to help us. If this is 75, we're going to use our little Z rule, and it's going to point to the angle that is also 75 degrees. So it's going to be the angle at the tangent that meets the chord is then going to be the angle that meets the circumference in the alternate segment. So we know because of our tangent that this is 90 and this is 90. So therefore the angle that is 75 degrees is this one here, the angle that we wanted to find out, ODC. So there are lots of different ways to be able to find out what that angle is. So we could have also used our rules. Let's look at another. A, B, C and D are points on the circumference of a circle centre O. AC is the diameter of the circle. AC and BD intersect at point E. Now all of this information they are telling us for a reason. CAB is 25 degrees and DEC is 100 degrees. Work out the size of angle DAC. Angle DAC is this one here. So let's look at where to begin. What we've got here is a diameter of the circle, which means the angle at the circumference, so CBA, this angle here, that's a 90 degree angle, because angles at semicircles are 90 degrees. So what we've got is 90 degrees plus 25 degrees, because ABC is a triangle. And then 180 take away 115, that gives us this angle here to be 65 degrees. And because angles at the same arc with the same segment are equal, that's to say ADB is also 65 degrees. Hopefully you can see that yes, here we've got the diameter, but it is also a straight line. So if that's 100 degrees, it makes that 80 degrees. And then ADE is a triangle. So that's 80 plus 65, which is 145. And then 180 minus 145 leaves us with 35 degrees. Was 4 marks. You need to show all your working. So you don't have to give reasons for each stage in your working, but you would just show the calculations that you are doing. Okay, let's try one more, and this is 5 marks. B, C and D are points on the circumference of a circle centre O. ABO is a straight line, and AD is a tangent at D to the circle. Centre O, so that is the centre of the circle, which means this line here is the radius, which means this is a 90 degree angle. So ADO is 90 degrees. Work out the size of angle BCD. So BCD is this angle here. So we've got to think to ourselves, how are we going to work out what that is? So if we just look at OBCD, and we look at this shape here, we want to at least work out this angle. Now we can do that because we know we have a 40 degree angle, we have a 90 degree angle. So 90 plus 40 is 130, 180 minus 130 that gives us 50 degrees here. Now, if this is 50 degrees, let's think of that rule. Angles at the centre are twice angles at the circumference. Here is our angle at the circumference that we want to find out, and here is our angle at the centre. So 360 minus 50, that's 310 degrees. And then we're going to divide that by 2. This angle here, 155 degrees. Now this one's so many marks because it's give a reason of each stage of your working. So, starting with ODA was 90 degrees as angles as a radius meets tangent at 90 degrees. Then we said ADO is a triangle. So we did 180 minus 40 minus that 90 to give us 50 degrees. We did 360 minus 50 to give us 310, which is angle at the centre. And then we did 310 divided by 2 to get 155 as angles at the centre are twice angles at the circumference. So it's important that you know how to write your angle rules. So what I can't write and say what I'm doing at the same time. At circumference, try that again. So it's important that we know how to write our rules using the language that we looked at right at the beginning on that poster. Any questions, let me know.